Hello, this lecture is called Vector Representations, and we are going to bring to light definitions concerning um, span and linear independence and basis. One important thing to remember about the span is that it's a set of all possible linear combinations of a given set of objects or things. So anything that's inside that set is going to be used into a possible linear combination, meaning that the definition of span relies heavily on the two operations addition and scalar multiplication as they are defined in the vector space where this set is being considered, right? So, and this is part of what we would like to discuss. So take, for example, this set with members v sub 1, v sub 2, all the way through v sub m. And if we were going to mention something like the span, the set that we call the span of B is a set defined by things that look like this. They are summations that involve beta sub k, for example, v sub k. And so here we would say k takes values starting at 1 and ending at m. Okay, so any member of the span is something that could be expressed as this summation, such that beta sub k is a scalar, is a complex number, and then v sub k is one of these vectors. So what we have here is that, you know, if we say that there is a vector w in a vector space V, then there are specific combination, there are specific values of scalars, and here's where you want to connect this, or also remember that uh, we first learn of span, maybe not by that name, when we were expressing members of the solution set, of a solution set, for a system of linear equations. So we could represent that solution as a summation of certain vectors, right? And so in that sense, thinking in terms of linear combinations, thinking also in terms of solution sets of linear equations, a solution would be a set of values, right? And in that sense, we were thinking of these vectors v1, v2, v3 as the columns of the so-called coefficient matrix of coefficients, and then the key thing was whether or not there were values for the scalars that would make a linear combination of the columns of the coefficient matrix to be something of interest, right? A specific quantity of interest. When we used to ask, is this vector a member of the span of this set? Then that question would be translated into a calculation of solution set, right? So all these things come into play. So, but basically what we're saying here is that W, that idea of membership, W belongs to the span of this set made of, right? This is the span of a set that contains elements v1 all the way through v sub m. So we know exactly how many of these elements. Specifically, we're saying this is a basis, right? So this also implies that the dimension of the vector space here is known. There are m elements on the basis, and therefore the dimension of V is known. And so another important thing to note here is that there is thing about uniqueness. The set of scalars, the values these scalars take, such that this is true, that W is a member of the span, well, that is a unique set of values. So it's analogous, this is analogous as to having a solution set that contains only one one vector, and having a linear system with that solution set, and we would say that linear system has unique solution. There's only one way of satisfying the set of equations of that linear system. So let's continue to consider this vector space V in basis, linearly independent set that's spanning. So any member, we say, you know, that we have a member W of V, then we can represent W as a linear combination of these vectors. I'm gonna now use different notation, maybe A sub j and V sub j. We change the notation here a little bit. So now this is, excuse me, this has dimension. This goes from 1 through n, right? So now the dimension of this vector space V is n. But if we say there is a member of such vector space, then that member can be expressed, can be represented. Okay, so this is a representation excuse me, is a representation relative to the basis B. So in terms of B, we could express that member of the vector space, the vector space V, like V as in vector. So in terms, maybe I should have chosen a different letter here for this to denote this set, is B for basis of the vector space V. Okay, so expressing that member of the vector space as a linear combination that involves these V1 and V2, because that's exactly what I've written here, is saying think of W as A1 V1 plus A2 V2 plus all the way through, sorry, I'm writing like this, all the way through A sub n Vn, right? So that's what this summation means. And so representing that arbitrary member of the vector space with this summation is basically making use of the members of that basis, and we need to know, each of these member of the sum is something that looks like scalar multiplication plus scalar multiplication plus scalar multiplication, right? And at the very end, scalar multiplication. Each of these is a column, so we're adding columns. If this were maybe I got a little too excited here. If these columns, if this were, if we had that V is C, I don't know, CM, for example, then certainly we're looking at a shape that looks like that. But the way this is proposed here is in more general terms. This is thinking of a vector space in general. However, we can, regardless of what a vector space V is, we can always define a function. Okay, we can always define a function that connects the arbitrary member of the vector space V with a representation in Cn. Okay, a representation in Cn. So, for example, suppose W in V. Okay, for W in V, we're going to define a column. You may be distracted here with the notation, but this row, this letter reads row of B at W. And so by thinking of this as a function from V into Cn, that means that when evaluated at a member of V, row sub B of W is indeed a vector with n entries. So we define such column vector in terms of the following. So what we really like to think of this is, so we were saying, think of this as A1, think of this as A2, think of that as A3, all the way through A sub n. So really, this sum here looks like A1 V1, A2 V2, A3 V3, okay, and all the way through A sub n V sub n. So the key is that now these coefficients, so we could also write, this is supposed to be little b, but so we could write this as A sub k V sub k, where k goes from 1 through n, where, and that is the key, A sub k is the kth entry of row sub b at W. Since row sub b at W is a member of Cn, so we know that this is something that looks like this, right? This would be a member of Cn, and so he would be the first position, the second position, all the way through the last position, and there are n of them, okay? So when we make use of rho sub b at w k, so we're referring to one of such entries on the kth position, right? The kth entry, something like that. And so that's the key, that these coefficients now are going to be defined by this operator, this function that maps the vector space V into the vector space Cn. So we are going to consider an example here with a vector in C4 with entries 6, 4, 6, 14, 6, and 7. And even though this vector is not going to change, the representations of this vector will change, okay? So let's consider a basis of C4, and the basis of C4 here has 4 vectors, right? So we're considering this as being U1, U2, U3, and U4. So the vector representation, right, that's what we want, this vector representation, that is precisely what this operator rho sub b is. And so that means that we need to find values of scalars, 4 scalars, for which a linear combination of these members of the basis B with those scalars would make this to be true. This is exactly the type of question of is Y a member of the span of B? And if it's true, it's because there are such values for scalars that make this true. So we can find such scalars because these values of those scalars are a solution to the linear system of equations that has the matrix of coefficients made of the columns. We use U1, U2, U3, and U4 as columns. If we form a matrix with those columns, and that would be the matrix of coefficients, and doing such calculation of solution set, we find values for A1, A2, A3, and A4. So these scalars, 2 for A1 and -1 for U2, -3 for U3, and the value of 4 for U4, these are the scalars that make a linear combination of those members of this basis B to be exactly equal to the vector that we started with, that vector Y. So what we do now is that we collect, okay, all those values, 2, -1, -3, and 4. We're going to collect those into we're going to store them into a vector, okay, and those vectors, those are precisely 2, -1, -3, and 4. These are precisely the values that are now stored into this column vector, and that is how we define this so-called representation. So this rho operator is denoting the vector representation, and this is the representation of that arbitrary member of C4 Y, but relative to specific basis of Y. So we simply collect those coefficients, the coefficients that make the linear combination true.